I'm Lars HAEUSLER. I'm researcher at the University of Freiburg, or more in particular the Intelligent Embedded Systems Lab. And one of this application we've been researching about, wanted to present today, is the application for activity recognition. Human activity recognition's task is to automatically identify human activities from sensor data, and it's important for different applications. As the name might suggest, we use sensors, wearable sensors, particular IMUs, so inertial measurement units. So this is one example of like a dedicated IMU, but now which has been placed here on the shank, and then we get two readings which are important for us. So we have the accelerometer first, where we get linear acceleration data, and then we also have a gyroscope, which gives us angular velocity data. Actual human activity recognition part is then the model. At the end, they can see this kind of data and then predict what activity has been done. So there's a lot of work in so-called synthetic IMU data. So we want to simulate IMU data instead of capturing everything. On the right is one other paper, right, where they wanted to impact which location is the best for one activity. And as you see, when you're working with this, you have like 396 physical IMUs. And it's a lot of work. We created one pipeline to synthesize IMU data. And the most important part for here is that it's generative. We use generative AI. Then the main advantage is now we can vary basically whatever we want to have a look at and whatever we want, right? So we can make different surface models. So in our approach, we can use any arbitrary position. So if you have the avatar here, it's a mesh with thousands of vertices, and we can use any vertex of that where we want to simulate how an IMU data, how IMU data placed on that location would look like. When we have these sensors integrated on our smartphones, we don't have our smartphones glued to our skin. When you have these loose placements, there's inertia, the fabric can wrinkle, stretch, or vibrate. So there's a lot of effects which has not then been modeled if we just place it on the human surface thing. And now we will do one extra step. So also we will have some gamma prediction. So then overall, this is the whole pipeline that we have. What we did, we created synthetic data sets. Particularly, we used 8 virtual participants. So what I said, the variations is we have 4 male, 4 female, and varied the sizes. So we have, and then we performed 6 activities 10 times. So we had each 10 descriptions. And we have 2 different fits to create overall 3 virtual data sets. We have tight fitting clothes, then we have the loose clothes here, and here again for a jumping pose we have tight on this side and loose on the right side. Sensor locations, so we use 6 locations in total, and for each locations we also varied the placement, so we have 9 different placements. With one practical example, so this is again our female average model with the 3 different from 3 different data sets at the actual IMU data, and then we compare the different fits. Overall, the data looks quite similar. The main patterns are recognizable over all the different data sets, but we have some difference, especially for the loose, which you can see we've dotted at the peaks. We have some deviations. So one thing that's immediately to see here is that's really depend on activity. So for static activities like sitting, we have really low errors for tight fitting and loose fitting garments, right? But if we have some more fast or high velocity activities like running or jumping, the error gets higher. So what we did was we trained a deep learning model. Actually, we trained different ones, 3 different, with the different data. So the first one is just for the body-mounted sensors, and then on the training, it just gets the synthetic data. Then we have one for the tight-fitted garments and loose-fitting, just the data from the loose-fitting. And what we did is we trained these models, and then we tested it on the actual public IMU data set. So we used one that was collected with physical IMUs, and then we tested on the whole data set and checked against the ground truth that we got. And right, so we get the body placements performs the worst, and the tight-fitting garments actually the best, and the loose-fitting a little bit worse, but still quite a lot of the body placement better. So to summarize, what we did, we showed that the text-based motion generation approach can be combined with garment prediction. And if we then have a look at the IMU synthesis, we see that it clearly affected the IMU synthesis if we use the garments compared to the body-mounted positions. Can be used for is to provide estimations before physical implementation.